So ACER's put out a new practice test called Practice Test A, and this is included in everyone's GAMSAT registration. So if you're sitting the GAMSAT, you'll have this test. And today I wanted to go through an entire work through from start to finish for this new exam. And really what I wanted to focus on was how I approach these problems and how I work through them. So I'd recommend watching this video with the questions. I'm not going to be able to have the questions on the screen. I'm just going to have to draw kind of what I'm doing or little schematics of the questions. So I'd recommend watching it with the exam next to you so you can kind of follow through with what I'm doing. In a separate video, I'll be reviewing how I did and then also going through some of the answer solutions if I got things wrong. But in this one, I really just wanted to show you how I actually work through them, as I think the process of actually getting to the answer is more important than the answer itself. Okay, so let's get started. So questions 1 to 3, we've got this biological pathway kind of thing by the looks. And then the question's asking, according to the table in the figure, indole would most likely build up in cells of what? So what am I thinking here? So when I look at the pathway, it says that this is basically a breakdown, or there's some conversion going on. But as I'm looking at it, I'm more thinking if something's building up, that means it's there, it's being produced, but you can't get rid of it. That would be my first thought for what's building up. So I see that we've got indole over here, and it's blocked off by well, it looks like the 4th step is the one that converts that to tryptophan. So that would build up if step 4 was broken. And then we need to work through what step 4 would be, because the question's actually asking for some mutant by the looks of things, because it's got tri, and then I can see that in the table it's got all the tri mutants in there as well. So we need to now look at this table. Now, what the table's telling us is that we've got these tryptophan mutants, and it says growth response on minimal unsupplemented medium. So how I'm looking at this, and I've seen similar questions to this in the past, basically that you've got this pathway and the thing at the end is what you need to get to actually have those cells survive. So I'm assuming that unsupplemented medium means that they die. And that, if we look at the table, that actually seems to be the case, because we've got all these tryptophan mutants here, and when we don't add anything else, when it's just nil, which is just the minimal unsupplemented medium, none of them grow. So this is telling me that if we don't give things, then none of them will grow. And that makes sense, because it means that none of them can get to the final product. So basically what happens when we give these things, so in the table it's saying we can either give T, I, A, or IGP. Now I'm not sure what these are, but I'll be able to find them. So T is tryptophan, I is indole, A is anthronylic acid or whatever. Don't know what that is. And then IGP is indole, glycerol, whatever. So basically it's saying, so if we look at all of them, so if we look at this first column, it basically says if we don't give anything, then all of them die. So that means that one step is broken. Now, if we look at the tryptophan column, they're actually all a plus, which means that all of them grow when we give tryptophan. Now, that to me makes sense, because I would say if we give the thing at the end, that's like what I was saying before, if we give the final thing, that's what they need to grow. So if we have them on the unsupplemented medium, they're not going to grow because they can't produce tryptophan. But if we give them tryptophan, it doesn't matter that they can't produce it because we're giving them the thing that they need. So if we then just start looking through all the other ones, so if we, now this one's interesting. So I'll do it down here. So we've got 3, 8, 1, 6, 7, 2, 4. And it's saying when we give indole, these ones, the first two and this last one grow, but this one doesn't grow. Now, I think that means that that's the correct answer because it means, remember, we need, for the cell to have a plus here, for it to survive, it needs to be able to make tryptophan. So if we were, so this is tryptophan down here, the final step. So if I was giving indole, but I'm still not surviving, it means I can't convert indole to tryptophan, which means that step 4 is broken. Now, if step 4 is broken, that, as we said before, that means that the indole is going to build up in those cells because we can't convert it to anything else. And it can go backwards, but I still think that that's where the indole would build up. So the answer for question 1, I'm saying, is A. Now I just need to write these down somewhere as well, actually. Sorry. A. Cool. All right. So number 2. So based on the information provided, which of the following is the most valid statement? So figure 1 could be correct because it does not contradict table 1, correct because a single and okay. I'm going to focus on B and D here because they're talking about single enzymes and I feel like I'll be able to rule that out. So single enzymes catalyze steps 3 and 4. So I don't see a reason why it can't be one enzyme. Oh wait, hang on. Catalyzes steps 3 and 4, one enzyme. I don't think, personally, I don't think it would be very likely that an enzyme would be able to do 2 separate reactions. So I think that steps 3 and 4 would be done by 2 separate enzymes because the main thing about enzymes is that they're highly, highly specific. So I would say that it can't be B. The figure can't be correct because a single enzyme catalyzes 3 and 4 because I don't think that a single enzyme would catalyze 2 different steps. Could be incorrect because a single enzyme could not catalyze steps 3 and 4. But I don't think it's saying that a single enzyme is catalyzing those. I don't think it's saying that because it seems to have these distinct, like 4 distinct steps, and then it's got 4 distinct mutants. So I'm actually thinking it's saying the opposite. So I don't really like D either. So it could be correct or could be incorrect. So it's basically saying, is it basically now, because I've ruled out those other options, I think it's just saying, does this contradict the table or not? So we've found out that try 167, so from the previous question, these 3 mutants, they seem fine because it's saying that that refers to step 4. Now, if I keep looking at that table, it's saying if we give indole glycerol phosphate, I'll have to make a new, just go down here a bit. Actually, no, I don't. I'll just stay up here. So now it's saying if we give IgP, it's saying negative plus, negative plus. So I think that's fine as well because it's saying that this one here, which we said was step 4, that makes sense because if step 4 is broken, it doesn't matter if you give IgP, you're still not going to grow. And then I would say that that means this one here, so this is step 4, This one I think is going to be step 3, because it means if we give IGP, it doesn't matter because it can't get through. And then the other ones, I'll just rub this out so I have a little bit more room. A, whatever that is, it's got negative, plus, negative, negative. So I think that's fine as well, because it's saying that this one has step 2 broken, because it doesn't matter if you give that anthranilic acid, it can't get past, but this one can. So this one must be step 1, I think. So I think it's a bit of a weird question, but I'm going to say for 2, A as well, because I think figure 1 could be correct because it doesn't contradict the table from what I can see. It seems like the figure's saying that there's 4 distinct things which could go wrong, and so's the table. All right, 3. According to table 1 and figure 1, the defect in try 3 could affect only. Now I just worked this out, so I'm saying step 3, and I'll just double check that. So if step 3 is broken, that would mean that it grows if you give indole or tryptophan, which is what we see, but it won't grow if you give anthranilic acid or indole glycerol phosphate, which is also what we see. So yeah, I'll say for 3, I'll say C. And now we can move on to number 4. Okay, so it took us a little while with that one, but that's all right. So, big table of amino acids. Let's have a look at this. So, the cleavage of which 4 nonapeptides, argipressin, oxytocin, octopressin, and cephalotocin, is facilitated by, which of the 4 is facilitated by the enzyme trypsin? So, you'll see that I'm always going to the question first because I want the context of what I need to understand first. So I really want to understand trypsin, and I wouldn't know that if I just read this question. So I'm basically just looking for trypsin, and I immediately see something that says trypsin facilitates at the carboxyl side. I'm not really sure what that means, of the amino acids lysine and arginine, if not followed by proline. So I love focusing on these details because I just feel like that's something which completely changes how things work. That's a classic thing to look out for. And it also says, if not immediately, I can't spell, if not immediately followed by proline. It also gives me something like chymotrypsin, but I'm not too interested in that right now. So if I then go up to so I have argipressin, oxytocin, octopressin, and cephalotocin. So, another reason, so it's going to say another reason why it's good to focus there, because they might give you more than 4, but there is actually only 4 here, so that's not saving us any time. So if I look in, so it's saying which ones will it cut. So argipressin, so I'm looking for a lysine. I'm just going to look for a lysine or an arginine, and if they have that, then I'll assess this rule later, but just trying to simplify it for myself at the moment. So argipressin has an arginine. Yes, and it doesn't look like it's followed by, so it does have a proline there. Okay, but it says the carboxyl side. So we've got this big string of amino acids, and then on one side it's got COOH, and on the other side it's got H2N. So I'm saying that the right-hand side is the carboxyl side. So it's saying it cuts at that side. And then if it's immediately followed by proline, which I don't think it is, because what we have in the argipressin is we have proline arginine, but it's cutting it this side. So if we're cutting it that side, I don't think it's immediately followed by proline. I think the proline would have to be following it on that side, because if you imagine, the enzyme is like here, the enzyme's like a pair of scissors. I don't see how it would be cutting here, but somehow recognizing something over here. So I think that it would cut argipressin. If we look at oxytocin, I don't see any arginine or lysine in there. So I think that's a no for oxytocin. Octopressin, I also don't see any arginine or lysine. And then cephalotocin, I see an arginine. And it's not immediately followed by proline. So I'd say argipressin and cephalotocin, which is answer B. Okay. Which amino acids could be isolated when chymotrypsin facilitates the cleavage of argipressin? So it's saying what, so if we just have argipressin and we have chymotrypsin, what would be isolated? So it says chymotrypsin, it's the carboxyl side again, but it's, so this is chymotrypsin. It's just the carboxyl side of tyrosine, tryptophan, and phenylalanine. Okay, so I'm going to get the codes for these ones. So, because this is another thing that I think is classic with ACER questions, they make them very close together in their spelling to confuse you. So we have TYR, TRP, and PHE. These are the ones for chymotrypsin. So if we look at argipressin, we have a tyrosine. What are my answer options? Okay. It says which amino acids could be isolated. Okay, so it's going to cut at the tyrosine. So we've got like a TYR, it's going to cut here. Then it's got a phenylalanine, so it's going to cut there as well. I don't see any other cuts. So all we're going to be able to isolate is phenylalanine. And the answer options are like tyrosine, cysteine. But I don't think we're cutting at the tyrosine, but that's not going to be by itself. It's going to have that cysteine next to it as well. So the only one you're going to be able to isolate, and I'm interpreting isolate as get on its own, is the phenylalanine. So that'll be answer A for 5. 6. What are the products when the cleavage of the known peptide cephalotoxin is facilitated by trypsin? So it cuts lysine and arginine. So the only one I see in there is arginine. So the answer options are saying a single, like dipeptide, tripeptide, whatever. So we're going to have we're going to be cutting on the right-hand side of the arginine again. So we're going to have cysteine, tyrosine, phenylalanine, and arginine in one block. That's 4. And then ASN, CYS, PRO, whatever, and another one. So that's 5. So I think it would be, tetrapeptide. Yeah, actually it would be tetrapeptide and a pentapeptide. Yeah, okay. So 6 is D. All right, scared myself there. I'll blame the dog. Okay, so suppose that for easier analysis, argipressin is to be broken into units no longer than tripeptides. To do this, trypsin, chymotrypsin, and one other enzyme are needed. this other enzyme should be able to cleave bonds at the carboxyl side of, okay, so I need no longer than 3. So what was it? It was argipressin. So currently if I cut argipressin, I would be cutting at the lysine, of which there is none, the arginine, of which there is one, so that would mean we get a GLY over here, and we get this big whole block with arginine there. Then we're also cutting at TYR, which means we're getting CYS at the start, TYR, that's all cut off. This GLY is cut off. And then we're cutting it, there's no tryptophan, and then there's a phenylalanine, which means we get the phenylalanine isolated as well. But it means in the middle, we have a GLN, ASN, CYS, PRO, ARG sequence. So we'd need to cut either here on the carboxyl side of ASN or on the carboxyl side of cysteine. So of those options, the only one which I think works is cysteine. Which one's glutamine? Glutamine's GLN. No, so that wouldn't work. So if we cut GLN, then we've got a 4 sequence. If we cut proline, again, we've got a 4 sequence. So yeah, the only one that works would be, of those answer options, is cysteine, but ASN would work as well. So that's answer option B. Okay. 8. All right. Scary looking cone and then a bunch of graphs. All right, so this is what I'd say typically would scare a lot of GAMSAT sitters. Okay, an electron beam, as electron beam energy increases, the maximum depth under the skin at which body tissue absorbs radiation. All right, so the first thing that I'm always looking for is I'm defining on my graphs what the variables represent. So electron beam energy, so what's that? So if I'm looking through the graphs, it looks like electron beam energy is MeV. And I'm not really, as you can tell by what I'm talking about, I'm not really looking at any of this stuff just yet. I'm just trying to keep it as simple as possible. So so it's basically saying as MeV increases, the maximum depth under the skin at which body tissue absorbs radiation is. So what am I looking for here? So it's something about absorbing radiation, like the maximum depth. So I see these graphs with depth below the skin, and then it's got these things. Are they percentages of absorbed radiation or something? It looks like it. Yeah, I think that's fair to say. So it's got PDD. What's that? PDD is the percentage depth dose. Okay, the PDD is expressed as the percentage of the maximum absorbed dose. Okay, so I'm interpreting that as the percentage absorbed. So it's saying the depth where you absorb radiation. So that's like the depth where there is still some radiation. So as I'm looking at these graphs, it's got these like, oscillating things like that. So I'm just going to take the lowest one as a measure of, even though that says it's 10%, I'm going to take that as the minimum because it'd be somewhere slightly lower than that. But as long as I'm comparing like for like, I can generalize that trend. So in figure 4, I have a 20 MeV graph compared to figure 3, which is a 9 MeV. So as I increase that, I can see the depth below the skin where we have that last kind of circle, which I'm taking as representing the minimum depth, sorry, the maximum depth, whatever, that's lower. So that's only at about 4 centimeters for 9 MeV. But when we go up to 20 MeV, it's at about 9 centimeters. So I would say the maximum depth. So the max depth increases. Then what does it say? The field size. So the field size, I would assume it has, I'm taking that because it has distance from central axis, and that's 0 in the middle there. So I'm taking the field length to be how wide it is. So if we look at figure 3, again, it's going from -6 to +6 on that distance on the x-axis. And then on the other one, it's not going much further, but it's probably going to about -7, -8 to +7, +8-ish. So I would say that that's increasing as well. So that would be answer D. The maximum depth and the field size increases. Okay. Suppose that compared to the figures shown, SSD is smaller, but STD is the same. Okay, what are these things? So SSD is smaller. Where's that? The source to skin distance, and then the source to tumor distance. Okay, and then it's given me this figure. All right, so it's given me this scary looking cone, and it's basically said that this is the SSD, and then the tumor's down here, and it's given me this, and this whole bit here's the STD. So the SSD is smaller, but STD is the same. For the 20 MeV beam, I don't think that particularly matters, to be honest. The edge of the field, I don't think it particularly matters that it's 20 MeV, but it's saying the A0, which is this bit here, compared to the AD, which is that area. So it's saying that SSD is smaller. So I'm basically interpreting that as instead of being where that yellow line is, I'm saying it's been brought up to here. Now, if it's been brought up that cone, that means that area is going to be decreased. If you have your cone like this and then you go up, that's a smaller area. So I would say that that is smaller. I'd say that area is smaller. But STD is the same. I think that just means I would interpret AD as being the same. I can't see a reason why. The only thing that's maybe throwing me is the 20 MeV beam, but I don't see a way how that relates, because the area is still going to be the same. I think I can't see a reason why I would not go with that. So we'll go with B for D. We'll go for B for 9. 10. Suppose that compared to the figures below, STD is smaller, but SSD is the same for the 20 MeV beam. So now STD is smaller, but SSD is the same. So STD is smaller. So the tumor is closer to the skin. So it's been brought up. So if it's closer to the skin, it means on our graph, this is getting a little bit messy, but we had all these lines which are referring to different depths below the skin. So it's basically saying instead of being these low ones down here, it's the STD is smaller, which means the tumour is not as deep. So that means it has to be one of these higher ones. So it means our the SSD is the same, which is the distance from the source to the skin. I don't think that changes anything because the tumour will still be not as deep in the skin. So the radiation dose will be increased. So because we're at one of these higher ones, so the PDD will be a greater percentage. It'll be, potentially the 90. Now, what will happen with the ISO curve? I think the ISO curve thing, which is figure 2, I don't see any reason why that would change, because to me that seems like almost it's just plotting the PDD at various depths. So that's not going to change. It's just like that's how much you would have at all those different points. So I don't think we're not changing that. The PDD is not going to change. We've got the tumour at a different depth, which means the PDD will be higher, I think. So I would say the ISO dose curve will be the same, but the radiation dose at the tumour will increase. So that will be answer option B for 10. Okay, 11 to 13. So again, we've got a little table. So which of the following is the best estimate of the value of H for 2-chloropentanoic acid? So we're really looking for a pattern here. So what's going to happen? So I want to look at I think I want to look at 2-chloropropanoic acid and 2-chlorobutanoic acid, because that's going to, if I extrapolate this pattern, that will give me a good estimate for 2-chloropentanoic acid. I think that's fair. So we have 45.2, and then we have 45.6. So that should be 46.0, I think. So I don't see any reason why it would be anything different. So 11 will be A. 12, which of the following is most likely to have a H value closest to 60.7? So it's got 3, so there's basically 3, 4, 5 pentanoic hexanoic acid. So let's see, so really I want to see the effect, I think, of changing the number out the front. So if I go from 2-chloro, so we kind of I'll just bring that back. So basically I could say from this, adding a carbon is like plus 0.5-ish of the H. So that's not really, doesn't have a massive effect. So I'll just leave that there, and just because I think it could be relevant because we've got carbon chains that are pentanoic and hexanoic. So we can see the effect. Now we know as well that 2-chloropentanoic, it was 46.1. So as we go from 2 to 3 with propanoic acid, for example, we go from 45.2 to 60. So that's plus 15-ish. So that would be pretty good. I think 3-chloro pentanoic acid, I think would be roughly, it should be like 61 or 62 or something like that. As we go, now if we look at butanoic acid, when we go from 3 to 4, we increase about 5 as well. So it won't be 4 pentanoic acid because that's going to be too high. Well, it's going to be higher than what we have, which I think is pretty close. 4 hexanoic acid, that's going to be too high. So all those other ones are going to be too high as well, because all of the changes there are going to increase the value. So that will be answer option A. Which of the following is most likely? So H, oh goodness. The value of H of all these very complicated molecules is less than, okay, so I'm just going to try to generalize these. So if I look at what's there, it doesn't really tell me any information about the 2-methyl. So as I'm just kind of looking at the general form of all these things, and it's got, a number, and then a chloro, and then a methyl, and then, a butanoic acid. Now, that's all the same. Well, sorry, the butanoic acid part is all the same between the two sides, so I don't need to care about that. Now, between the left and the right, it's got, it changes this number as well before the methyl, but I don't have any data, I don't think, for the effect of adding a methyl group somewhere in the chain. So I'm actually for now, I'm just going to ignore that. And I'm just going to focus on the chloro part. So we know the effect of increasing that number on the chloro greatly increases the H value. So if we look at 3 chloro compared to 2 chloro, that would be higher. So I think I can rule out A. With B, I would say that looks true because 3 chloro should be less than 4 chloro. 4 chloro should not be less than 2 chloro, so that rules out C. And then for D, 5 chloro pentanoic acid, no, because it's got a higher chloro number and it's got more carbons, which also increases that. So it won't be D. So I think I can say pretty confidently that it will be B, that 3 chloro will be less than 4 chloro. And I've just kind of ignored all the other information that they gave me because I don't think that that's going to have as big an effect as the number out the front of the chloro. Okay, so I have seen this question before, but I can't remember the answers, which is good. So I also seem to remember struggling with this one, so that's not good for me. Okay, from hypothesis 1, it can be concluded that the offspring of a cross between Japanese starry flounder and right-eyed West Coast starry flounder would be. So hypothesis 1 states that Japanese fish are homozygous for dominant left-eyed allele. Dominant left, okay. Whereas West Coast fish are homozygous for a neutral allele and have equal chance, which is 50-50 left or right. So I'm just going to take this as true, I think, because it's saying that that's the hypothesis. So what would happen? So we would have a cross between these, so we'd end up with all that. Now, now it's saying that that's dominant. So I think for 14, there would be left-eyed flounder only because the left thing is dominant. So that would be C. 15. According to hypothesis 3, many crosses between, okay, it's a bit scary. So what's it saying? So it's saying that we're crossing this thing with this thing. I might change these letters because they're a bit scary looking. Hypothesis 3. there are 3 alleles controlling these. So it's saying that left is dominant to right, which is this, which is dominant to neutral, which is that. Further, the right allele is, oh wait, no, I've already read that. Oh yeah, okay. Fish that are homozygous neutral is 50-50, left or right. So I'm going to simplify this for me a little bit and just say this is like a right neutral with a left neutral. Just confirming I've got that right. Yep. So we're going to have left right with left neutral, right neutral, neutral neutral. So this guy's going to be, these two are going to be left because that left is dominant to everything. Right's dominant to neutral, so that's going to be right. And then this one is going to be neutral neutral, which is 50-50 left or right. So basically we're going to have 2 left, 1 right, and then 1 50-50 left or right. So it's basically like 2.5 to 1.5. I don't like how I've done that. I might just double these. Yeah, I might double these. So this 1, I'm going to split between both of these because it's 50-50 left or right. So you don't know, it could be a left or it could be a right. But I'm just going to average it out and say that it splits evenly amongst the two. So it'll be 2.5 left to 1.5 right. But then if we double that, that's 5 to 3. So 5 to 3, it's like 5/8 to 3/8. So it's like a bit more than half. So that would be C for 15. Maybe a bit of a messy way to get to that answer, but main things you get to the answer, I guess. Key things just like making those numbers make sense. Like if you get a little bit stuck, you just got to have a way that you can work through them. Consider hypothesis 2. Okay, the Japanese fish are homozygous for left. This is Japanese. Whereas West Coast is just 50-50. 50% left, 50% right. Homozygous equals, heterozygous, sorry, equals 50-50. Messy notes, I know, sorry about that. Okay, so consider hypothesis 2. Assume equal frequencies of left and right alleles in the West Coast population, and that there is no impediment to the occurrence of any genotype. From hypothesis 2, it can be concluded that many crosses between the Japanese and the West Coast would be. So again, we'll have left, left. And I'm just going to say that we have 50%. Okay. Well, here's what I'm thinking. So you've got basically, it's like you've got 10 left alleles and 10 right alleles. And they can form whatever they want. So you could buddy these up and get a left-left, or you could buddy these up and get a right-right, or you could have one from each, which would be a left-right. But overall, I don't think that's going to matter because like I could do 3 crosses here between all 3 of these because these are all going to be in equal proportions. But I don't think I need to because this is going to be all left. Well, maybe I'll just do it. It's not going to be that hard. This is all going to be left, right. And then this is going to be 50% left, left, 50% left, right. So I'm going to get, yeah, so those two don't matter because I'm going to have either way, when I look at all these, I'm going to have 50% left, left, 50% left, right. Once I aggregate it all. Now, it's saying that left, left is dominant. Well, it's going to be left. And then left, right is 50% left, 50% right. So it's going to be like 50% left. And then of this 50%, 25% are going to become left and 25% are going to become right. So overall, we're going to have 75% left, 25% right, which will be 3 left-eyed flounder for every 1 right-eyed flounder. Because, yeah, you have half of them are going to be left, and then the other half of them are going to be left. It's a little bit confusing. I hope that makes sense. And then when a left-eyed Pacific female and a right-eyed West Coast male were crossed, the offspring kept in a standard laboratory conditions on the west coast of the USA. 50% were left. Oh gosh. 50% were left, 50% were right. What does this rule out? If I take hypothesis 1, that's dominant. So it'd be LL. And then the West Coast fish are homozygous for a neutral. So all of my progeny are going to be left neutral. Now it's saying that I then leave them in the West Coast, which means we're going to be crossing them with more neutrals. So after all of these divisions, I'm going to have 50% left, and then these, again, 50% are going to go left, but 50% are going to go right. So that won't work. Yeah, I think it rules out hypothesis 1, because you'd get 75% left, I think. Hypothesis 2, the Japanese fish are left. The West Coast fish are left-right and occur in equal proportions. So you'd cross these, you'd get left, and then left, right. Oh, am I going to get the same thing? You'd get 50% left, 50%. Oh, I've done something wrong here. I'm going to say it rules out hypothesis 1, because I think that you're only going to get this, and then if you cross it with that, you're never going to get rid of this allele. So I think hypothesis 1, but I'm not very confident with that one. I think I might get that one wrong. Okay, so moving on to 18. So we have another graph, and it's saying, according to the figure, it is likely that significant amounts of antibody to day 3 trypanosomes. Okay, so what the hell's going on here? Okay. All right, so I've got this graph, and it's saying the agglutination titer, which would happen if you had antibodies. If you had antibodies to that thing. So it's saying there's trypanosomes. They bit the rabbits. It's a bit grim. They bit the rabbits, and then they took blood samples from the rabbits over the next 22 days. So they took that plasma, and then they took the trypanosomes from each of these days. Okay, so it's basically saying, did the rabbit have antibodies or not? So significant amounts of antibody to day 3 trypanosomes first appear in rabbit blood during day. It's like day 6 or 7, because that's when the day 3 trypanosomes go up. So yeah, I'd say day 7-ish, something like that, of the answer options. Okay. On day 15, the rabbits had the greatest immunity against. So basically the one with the greatest antibody titer, I would say. So that'd be day 4, trypanosomes. So really, it's actually quite an easy graph once you get your head around what each thing represents, I think. So the greatest immunity would just be the one that you have the biggest antibody response against, I would say. The reaction between day 3 trypanosomes and the plasma collected from the rabbits on progressive days from day 7 to 9 inclusive increased because, so it's just saying between 7 and 9 it goes up. Why did it go up? The level of rabbit plasma antigen increased. No. Trypanosomes increasingly produced more antibody. No. The level of antigen on day 3. No. Antibody against trypanosomes increasingly appeared in the rabbit's blood. Yes. So that's what the agglutination titer is. It says that that's what happens when there's an antibody reaction. It says that in the text. So the greater the specific antibody reaction, the greater the titer. So it's saying the greater the antibody response. According to the evidence provided, which one of the following best explains the alternation between episodes of severe and mild symptoms of sleeping sickness? So what's that? Okay, typically, so I'm just looking for specific information about that. So when there are high levels of trypanosomes in the blood, there are more severe symptoms. Makes sense? And when there are fewer trypanosomes, it's milder symptoms. So if you are alternating between severe and mild, it means that you're clearing them, but then they're coming back. So the immune system is damaged by trypanosomes. I don't think so, because if you damage the immune system, then it should just increase, but then it wouldn't be able to come back. Trypanosomes has evolved to become resistant to the antibiotics used against them. I don't think it's antibiotics. That could be correct, but because I think that would actually have the effect that we're thinking. Actually, then, because if they become resistant, again, that will mean that they don't come down again. So I think that's wrong. But I think the other thing I was going to touch on is that I think it's more about the antibodies, not the antibiotics used. The antigens on the trypanosomes in the blood undergo periodic changes. I think that sounds correct. When ill, the victim of sleeping sickness is periodically infected by new microbes. No. So C for that. Because if you're changing your antigen every now and again, if you imagine that, basically the body recognizes the antigen. So if you've just made all these antibodies against that and then you change it, then you can't recognize it, or the antibodies can't bind. So that's why the agglutination titer would come down. Okay, 22 to 24. In a material containing container, the water activity represents the proportion of water, blah, 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 blah. Okay, gives me some values, got these formulas. Okay, so a food product with an MFSL of no more than 1 day has an AW of what? Okay, so MFSL, so it's saying that the MFSL equals 10 to the 9.5 minus 10 times AW. Now, it's saying that the MFSL has to equal 1. So for that to equal 1, that would have to be 10 to the 0, because 10 to the 0 equals 1. So basically, we need to make this top part equal 0, which means that we have 9.5 minus this part here needs to equal 9.5. Now we have 10 in there, so it has to be 0.95, because then times 10 will be 9.5. That'll equal 0. And then it's saying at least 0.95 or 0.95 at most. So if we increase this, it'd be 1 times 10, for example, which would be 10, which means the number here would be 9.5 minus 10, which means we'd have 10 to the negative 0.5, which is good. That will be less than 1. Yes, because that would be like the square root. Oh, actually, hang on. Yeah, I think that's good. Whereas if you had a lower number, so yeah, so if we increase that, higher number means a higher number here, means we're subtracting a higher number, which means our index actually becomes lower, that's a good thing. Whereas if we went the other way, if we decreased that, then it'd be like 0.5, for example, times 10 means it's 5, which means it's 9.5 minus 5, which is like 10 to the power of 4.5 all of a sudden. So we don't want that because that's like 10,000. So we need a minimum of 0.95, which is at least 0.95, which is 22, so that's C. All right. 23, a jar of jam has an AW of 0.88 and an MFSL of 5 days. By how much must the AW reduce in order to double the MFSL? Okay, so we've got 5. Well, actually, I don't even think I need that. So we need to go from 5 to 10 is basically what it's saying. So 10 equals 10. That means we need this to equal 1, basically. Is we need that, because remember our formula is MFSL equals 10 to the 9.5 minus 10 times AW. So for us to, so it's saying that the MFSL is currently 5. To double that means the MFSL has to become 10. Now for the MFSL to be 10, we need 10 to the 1, which means that that index up the top needs to equal 1. Now we've got 9.5, so for that to equal 1 to give us the MFSL we need, it needs to be minus 8.5 in the brackets. Now the thing in the brackets is times 10, so it means the AW needs to equal 0.85. Now it's saying that the AW is currently 0.88. So we need to reduce the MFSL by 0.03, which is A. 23. Cool. Which of the following is closest to the AW for products with an MFSL of 3 years? Now this is actually, I didn't actually check this, but I should have, I should have checked that the MFSL was in days, but it is, because the previous ones we were looking for days, so we could have had a fraction there, but I got away with that because it is in days, but now we have a MFSL of 3 years. So that would be 3 years times 365. I'm just going to say that's roughly 1,000. I think that'll be fine. So we need MFSL to be 1,000, which means we need 10 to the 3. So index laws are just so important. Index laws and scientific notation is just a must. You need to have that. So I'm assuming, I think that should be fine. So we need 10 to the 3. So again, using our formula, to get 10 to the 3, the number within the brackets, because it's 9.5 minus the number in the brackets, we need 6.5 in here. Again, that's going to be multiplied by 10, so it's 10, we need an AW of 0.65, which is exactly the answer C. So I'll put that in there. And I will just have a quick, think about if it would be, it's not going to be any of the other ones. Because if it was, for example, 5, 5, then this would become minus 5.5. So I might just have a think about this if I was in the exam and just see what that would do. But this would make that 4, which means this would become 10 to the 4, which is 10,000. So that's going to be way too much. So, yep, so the answer will be C. Okay. Question 25. So, which of the following is the closest to the diameter of the radio bubble? So it's saying that we started broadcasting signals into space 100 years ago, and there's now a bubble of television signals. They travel, okay, so in 1 year, they travel 10 to the 16 meters. So now it's saying the diameter of the bubble. So in 1 year, 10 to 16, so 100 years, we'll just be timesing that by 10 by 100, that'll be like 10 to the 16 times 10 to the 2. And then that's 100 years. But remember that we would be shooting these signals out in one direction. So it means it's gone 10 to the 18 meters this way, but it also means it's gone 10 to the 18 meters that way. So it'd actually be 2 times 10 to the 18 meters for that one, which is answer B. Okay. Now, it would be difficult for any extraterrestrial life to detect these signals because the signals lose intensity at a rate inversely proportional to. Now, I have a formula for this, which I think is I don't have many about signals intensity, but I think there's one: intensity equals the power over the area. So the area is obviously going to be pi r squared. So I don't have a great reason for this, but I would just say, so the intensity, you lose the intensity inversely proportional. It seems to be fitting quite well. So I'd say the radius of the radio bubble squared. I'm not extremely confident with that, but I just know that formula. A lot of physics for me, if it requires that knowledge, I'm happy to just write that off as a loss. I'm aware of that. I think that formula is right, but there could be something else in there. But I'm just kind of trying to think of something where it has the radius. That's really the only formula I know anyway. So I'm happy to get one wrong. And then 2 signals of the same frequency transmitted from Earth. Q has 100 times as much energy as P. Suppose there is a minimum intensity. So I think that might work, my formula, actually. So the minimum, so it's basically saying the intensity has to be the same. But this is how I interpret it. If it's saying there's a minimum intensity, it's like if I need 2 liters of water to survive or something, and someone else needs 2 liters of water to survive, we both have the same minimum amount of water. So therefore, if there was an equation that equals that, like I guess what I'm trying to say is I'm always looking for ways that you can just make formulas equal each other. So we have this intensity equals power over area, and we have 2 different things. So whenever you have 2 different things, you really want to be thinking, can you relate them together? Now I'm saying because they have the same minimum intensity, I'm interpreting that as we can just make, I don't see why we can't make them equal the same thing, because this equals the intensity, and so yeah, so it equals the same thing. Like if this minimum was 1, then the other one has to equal 1 as well. So because they both equal 1, we can actually just say P over A equals P over A. So this is something that I use all the time. I'm always just looking out for that. I didn't explain it very well, but hopefully that makes sense. So if I say that this side is P and this side is Q, then it's basically 1 over the area equals 100 over the area. So Q should be able to be detected. Now it's saying the distance, not the area. So this is pi r squared. This is pi r squared. So I'm just going to get rid of pi because it's the same on both sides. So that will be, so if I just make this work, this radius will equal 1 because 1 squared will equal 1. So then that equals itself. And then for this one, 10 squared will equal 100. And therefore the top equals the bottom. So that's how I'm interpreting that. So it'll be 10 times as far as P, the radius, so that'll be B. All right. Cool, so more graphs. The spectrum shown above could be that of an equal mixture of 1 and 2, whatever they are, okay? So it's basically just got these different shapes and it's just saying which graphs could it be? Okay, so we've got this, we've basically got, if you look at the graph, we've basically got this big absorbance thing. It's got 4 different lines in there, all these different shapes. And then it's given us a shape and then said which of these 4 graphs have been used to make this one. That's how I'm interpreting it. Now, this part of the graph in question is at roughly 700 wavelength and it's 0.5 absorbance. So when I look at, so that's probably the most distinct thing to me is what has that value. And the only one which has that value is 2. Number 4 is the only other one that it can be, but that doesn't get up to 0.5. So I think it has to be 4. We have to have 4 in there because that's this portion. So if we look at 4, is it 4? No, sorry, 2. 2. So we have to have 2 because that's the only one which gets up to that height there. So that means that accounts for the little peak. So we have another little peak here, but that's accounted for by 2, I think. So the only part which isn't accounted for by 2 would be the little bit on the left. And that's 400.4. I don't quite understand why it's not lining up. I mean, I guess it's just experimental error or just, device error or something. I'm not sure why they're not lining up, but I can't really think of a reason why. So how do I pick between 1 and 4 here? There should be a reason why these graphs aren't lining up. And I think it's going to be something like you've already got, maybe it's the absorbance of maximum, 40% of the max. I'm not sure because it doesn't go up to 1. The only thing I'm going to go off is that the intersection of the line where this line crosses over, in the figure with all the graphs, it's, for the blue line, it's slightly under 0.2, whereas the red line slightly over 0.2. And then in the graph we have, it intersects slightly under 0.2. So I'm not very confident in that. And also it's lower. It's lower, so I feel like that could maybe make sense. So I'm not confident in that one at all, actually. But I'm going to say 2 and 4, which is answer C. So that was a tricky one. I'm not sure what I missed there. Suppose there is a reaction in which one of 1 to 4 spontaneously converts to another one of 1 to 4. If the absorbance at 500 increases as the reaction progresses, what could the reactant be? A reaction in which one of them converts to another one at 500. So if I'm looking at the thing at 500 and it increases as the reaction progresses, what could the reactant be? It could be 1, it could be 4, it could be 2, I think. The only one I think it can't be is 3, because 3 is the highest absorbance at that wavelength. So any of them could increase except for 3. So I think that one's D. The following graph shows for a reaction the absorbance spectra of the combined reactants and the combined products. Which of the following is best supported? 3 and 4 are reactants, 1 and 2 are the products. So it's increased in absorbance at 500. Reactants have gone to products. So it's gone from, the only one it could be at is 2 to 3. I think that's the only one that seems possible to get that jump at 500. It's kind of similar to the graph that we had here. There's a line, there's like a little one down here, and it's jumped up. So the only one which could do that with that shape is 2 going to 3. So I think 2 is one of the reactants, and 3 is one of the products. And then the only one where that works, oh, there's another one, D. So the reactant is also one at like 700. It's quite high. That could be due to number 2. So this is confusing because if 3 is one of the products, then why is there no absorbance? Oh no, that makes sense. There's no absorbance spectrum there. Okay, cool. So it means we can't have 4. So we've got this, so now the thing I'm looking at here is that at the end, we've got this as the reactant graph, and then the products are completely flat. So if the products are completely flat, it means we can't have 4 as a product because 4's got a little spike here. 4. So 4 can't be a product. We know that 3 is a product. So the only answer option with 3 as a product is option B. The only one with 3 as a product which doesn't have something else which will spike at that 700 spectrum is option B. Right, in a mixture of 1 and 3, such that each contributes equally to the absorbance at 480, .480, 1 and 3, there are contributes equally. Okay, so it's saying how much higher is the absorbance. 1 and 3 at 480. 480, 1 is at like nothing. So like 0.1 or something. And then 3 is at 0.8. So I'm going to say I hope I'm not falling for a trap here, but I'm just going to say that there has to be 8 times as much of 1 as 3. Just because if you had 8 times as much, if it's absorbing 0.1, if you increase that, surely then it'll increase it. So that's D. Okay, 32 to 36. So which of the following statements about the observations is least supported? So increase in fat mass is related to total energy. So I like looking through the options as well to kind of describe that. So it's basically saying is, so we've got one option which is like fat mass, which is related to total energy. Lean is related to total energy. And I'll just look at those two. Where is total energy? So I don't think you can really look at that because all of these had 140% of the total energy required to maintain that, and all of them have different changes in. Well, actually, fat mass. Yeah, so fat mass increased. Yeah, so fat mass increased. Correct. So that is supported. I always confuse myself with these double negatives. So increase in lean mass is related to increase in total energy intake. I would say yes, because 2 of the 3 groups had an increase. So the other one, there's probably some reason why the lean body mass decreased there. Change in resting energy expenditure is related to increase in protein intake. So I approach these tables a lot like a graph, really. I just look at single variables in isolation. So resting energy expenditure is related to increase in protein intake. Well, no, because no, it'd be the other way around. You change your, so if you look at that, there is lower protein in that group which has lower resting energy expenditure, but it's like what's causing what. So so it actually could be C, because I don't think that one's confusing me. Change in resting energy expenditure is related to increase in protein intake. Well, that's supported, I think. If you increase your protein intake, it'll change your resting energy expenditure. I'll leave that one alone for a little bit. Change in non-resting energy expenditure is not proportional to increase in total energy intake. So non-resting energy expenditure, the change is not proportional to increase in total energy intake. I don't think it is. No. No, it's not. So that is supported. Gosh, I hate these double negatives. So the change in the non-resting energy expenditure. So I can see that it's lowest over here. So I'm just trying to keep it simple. Highest, and then like high over there. And then the total energy intake is highest, high, and then lowest over here. So it's not proportional. So it's not proportional, so therefore that is supported. I think I've already said the other two are supported, so I'm going to say C for that one, especially because that one just made me feel a bit, I wasn't completely sure. It sounded wrong. Okay, the difference in changes in lean body mass observed across the 3 diets is likely related to, so lean body mass, so this is the one I was looking at before. So this is the one which had a massive decrease in diet 1, but the other 2 were big increases. So the thing that stands out to me here is the resting energy expenditure, and then also the non-resting energy expenditure as well. the energy intake, that doesn't seem to be the reason for it, but there's also total energy expenditure is way down. So, but it's likely to be related to the amount that we're getting from protein, I guess, because that's what's significantly decreased. Because there's also, it could also be fat because there's more fat, but which one is it? So let's have a look for something else. Diet 2 was considered a normal diet. Oh, it's lean, non-fat body mass. So it's got to be the percentage of energy from protein. So I had an assumption that it was protein, but I just didn't want to rely on that assumption. So I was just looking for evidence, but I think that's evidence is that the lean body mass is non-fat. So it's likely to be related to the percentage of energy from protein, I think. Which of the following provides the strongest evidence for the statement, calories alone account for the increase in fat mass? The strongest evidence. Now, all of these diets have 140%, and all of them increased in fat mass. So I would say the increase in fat mass across all three diets. Yeah, I think increase in total body mass resulting from diet 1. No, I don't think so. Or total body mass from diet 2, no. Because they all went up. They all increased heaps, and the fat mass increased heaps. So the only thing that was constant across all three was the total energy intake. So I would say A for that one. All right. Which of the following is the best conclusion from a comparison of the changes in energy expenditure across the three diets? So total energy expenditure depends only on total energy intake. No. Because they all had essentially the same total energy intake, but the energy expenditure was massively different based on the diet composition that they had. So that's not a good conclusion. Resting energy expenditure depends only on total energy intake. Again, no. Deviation from normal in the intake of protein limits physical activity. I think that's yes. Deviation in the intake of carbohydrates limits physical activity. No, because the carbohydrates were relatively similar across there. But when we significantly change from normal the protein, then we do seem to, because non-resting was the total energy minus the resting energy. So that's basically physical activity. So we do more physical activity. We do less physical activity. Yeah, we do less physical activity when we change the protein. Either way, increase or decrease. Yeah, so 35 will be C. And then which diet group had the greatest increase in energy intake per kilogram of starting body mass? Now, I don't think we don't have it has the average mass at the start. So we've got 69, 78, 76, something like that. And then it wants the greatest increase in energy intake per kilogram. Greatest, okay. So they all increased They all had 140%. Hmm. I'm I'm gonna go off that 140% rather than the total energy intake, because we don't know what the starting energy intake was, other than 140% of the total energy required to maintain stable body mass. So I'm going to go off that 140%, and therefore I'm going to say that these guys had the most. Diet 1. They had the greatest increase because they had the same percent as everyone else, but they were lighter and smaller. All right. Question 37 to 40. So we've got this person jumping on the moon, and it says, consider jumps on Earth and the moon. So a person will only leave the ground, and then it says on Earth if blah, 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 and on moon if blah, blah, blah. So with anytime I've got numbers in an answer option, I'm always looking for how I can squeeze that into an equation. So it said a person will only leave the ground. So what does that mean? So it's telling me that J equals jump. Who would have thought? So if they're jumping, that means J has to be greater than 0. That's basically how I'm interpreting that. So I've basically interpreted the sentence, a person will only leave the ground, as basically when will J be greater than 0? And they've given me, the other thing I was looking for J is they've given me these equations with C and K in them. So if we want, so it says a jump on Earth, so it's basically saying when will that be greater than 0? So we've got C, which is how far they lower their center of mass. So another good thing with equations that I like doing is just ask yourself, can you just ignore it? So I think I can just ignore that because I can just make it 1. So that's a very common thing I do, is I try to just say, can I make it equal 1? Because anything multiplied by 1 just cancels out. So it's nice and easy. So I don't see a reason why I can't say that they crouch 1 unit, whatever that is. So let's just ignore C. And that means my equation just becomes KE minus 1. So they will jump on Earth if KE is greater than 1. If it equals 1, we get 1 minus 1, which equals 0, which means the jump will be 0, which means they haven't jumped at all. So my KE has to be greater than 1. And so I'm liking the look of B, because it says, so we've got the same equation for the moon. It says J moon equals K moon minus 1. Again, I've just cancelled out that C. But it's also, because it said that the gravity on the moon is not as strong as Earth. So they've also given us this other equation, minus 6K minus 1. But I think because I've got 2 equations, if Km was greater than 1, Jm would be greater than 0. So that works, I think, which is option B. I'll just look through the others. So A is wrong because it's got K Earth and K Moon as equaling 1, which means it's going to be 1 minus 1, which equals 0. So they're both wrong. C is wrong because it's got K Earth equals 1. So that would mean the jump on Earth is 0. And then D says on Earth, if K Earth is greater than 1, so that's a tick. But on the moon, only if K moon is greater than 6. And that's not true, because if K moon is greater than 1, you'll leave the Earth. So if it's greater than 6, they will jump, but not only if it's greater than 6. So for 37, I'm going to say B. Now, 38. suppose that a person jumps 11 times as high on the moon as on Earth when using equal force. How large is the force exerted by the person jumping? So again, let's just try to put some things into variables. So it's saying J moon is 11. Well, I could just say that's 11, and J Earth equals 1. Now, I don't quite know how I'm going to get to that force, but I feel like I can, like, kind of similar to that other question that I was doing before, is I'm trying to make these equations equal each other in some way. It's a very common way to solve these problems is to, you make them equal each other and then that gives you one variable rather than two. So I'm thinking if I can sub that in maybe. Well, what if I just solve this? So J Earth equals 1. So 1 equals C, which I'm just saying is 1. To cancel it out, equals K Earth minus 1. So K Earth equals 2. And if I just do J, so if I do 11 equals 6KE minus 1, so it's going to equal the same thing. So I don't really know what I've calculated here, but if I move that 1 over to the other side, it's 12 equals 6KE, and then KE will equal 2. So I'm not really sure why I did that twice. I thought I was going to have to make them equal each other, but K refers to, so if I look at the force equation, it's got K mg, and it's talking about their weight. So m times g is that's going to be their weight because it's the mass times gravity. So I'm just going to say twice the person's weight on Earth because I've got Ke equals 2. So E for Earth, it's going to be like Ke is going to be here, so it's going to be 2 times mg. So I think, so I'm trying to make sense of it. I can't give like a really good explanation for why I'm saying that. It's more just trying to make the numbers work, and I don't see a reason why that isn't correct. So I'll say C for that one. Okay, consider a person who jumps on the moon using a force that is 6 times their weight on the moon. If the person uses equal force on Earth, they will. So they jump on the moon 6 times their weight on the moon. A force that is 6 times their weight on the moon. So that means I think K moon equals 6. Yeah. So J moon equals, oh wait, hang on. So I need to find the equal force on Earth. So I think what I actually need is KE because I want to know how high they will jump on Earth. And the only way I can find J Earth is by getting K Earth. So so it's kind of like a bit of a puzzle. It's like what variables do you need? So I think I need to get KE. So I think I can relate the two formulas. So I know that I'm going to cancel out C again. So Km minus 1 equals 6Ke minus 1. So again, they're both minus 1, so we'll just get rid of that. So Km equals 6, which means that Ke will equal 1. Now, if Ke equals 1, Je equals Ke minus 1. So if that's 1 minus 1, that equals 0, which means they don't leave the ground. So that's A for 39. And then for 40, consider a planet with 1/3 the gravity of Earth. For jumps using equal force on the other planet and on Earth, which of the following is correct? So it said that it says that the moon is 1/6 as strong as Earth. And that's why we've got the formula J moon equals 6 KE minus 1. So if I say that we've got this other planet, J planet, it should be 3 KE minus 1. And then the jump on Earth is just KE minus 1. So I'm just going to get rid of all these minus 1s because it's all the same for all of them. So the jump on the moon will be 6 times. So let's just put a number in here. So we'll just put in 1. And I know that I just said 1 equals 0, but whatever. We've cancelled off that -1 thing. So if KE equals 1, that means the jump on the Earth will be 1. That means the same KE on this planet will be 3, and the same KE on the moon will be 6. So now I need to go through and it's saying, what will these jumps be? So it said that J moon over J planet greater than J moon over J Earth. So let's put these numbers in. So it's like 6 over 3 greater than 6 over 1. That's not true. So it's not A. Then it said that J moon over J planet less than J moon over J Earth. So yeah, that's correct. So that's B. And then if I just go through the last two answer options though, so we've got J moon, which is 6, over J planet, which is 3, equals 1 over 3 times 6 over 1. Is that right? That's also correct. 1 over 3 times 6 over 1. So 6 over, I've done everything right. J moon over J planet. Yep, 6 over 3. 1/3 times 6 over 1. So that's also correct. Okay, that's a bit concerning. J moon over J planet equals 2. 6 over 3 also equals 2. All right, what have I done wrong here? So I've got 3 correct answers. J moon over J planet equals 2. The jumps using equal force on the other planet and on Earth. So let's just reevaluate what I've done. I've clearly done something wrong. 6 KE minus 1. Maybe that minus 1 does actually have an impact. So let's do that with the minus 1s. So let's say that KE equals 2. Because maybe something's gone wrong. I don't see why, but maybe that's made this go wrong. So we've got 2 minus 1, which means this equals 1. Oh, this is gonna this is gonna change things. So 2 times, that's 6 minus 1. So J planet is 5. And then we've got 12 minus 1, which is 11. Okay. So we've got 11, 5, and 1. So that was important information. So I know answer A is still going to be incorrect. So I'll just ignore A. So B, I think, is still going to be right because it's saying that 11 over 5 is less than 11 over 1, which is correct. C is now 11 over 5 equals 1 over 3 times 11 over 1, which is not true because that's 11 over 3. And then 11 over 5 equals 2. It does not equal 2. So the answer here is B. So that was bad of me to try to take a shortcut. But we got there in the end. That's the main thing. Okay, questions 41 to 43. Many synthetic dyes are based on azobenzene, whatever that is. Which of the following groups, if attached to the benzene groups, would not increase the wavelength at which the maximum absorption occurs? All right. So the greater the number of such groups in a molecule, the longer the wavelength of light is absorbed. So increased number of groups, whatever they are, equals increased wavelength of absorption. All right. Now it's given me all these groups, and it says that these groups are ones that contain conjugate bonds. Conjugate bonds are structures containing alternating single and multiple bonds. So it's given me like an example of like a single and a double. The multiple bonds may be double or triple bonds, occur between two carbon atoms, or occur between, so it can be between, so it can be carbon to carbon, or it can be carbon to oxygen / nitrogen. And it's given me some examples. Okay, so carboxylic acid group, that would, I'm going to say that would increase it, because carboxylic acid will be C double bond O. So that's going to increase the conjugated groups. Nitrile group. Don't know what that is. Nitrile. Doesn't sound right. Alkyl group. Aryl group. Now an alkyl group would just be like single bonds. Like an alkyl is like ethane or something. So that's all single bonds. So I don't know what a nitrile group is, but I'm actually going to say that an alkyl group will not increase the wavelength, because I think that's all single bonds. I've seen aryl around the place. I think that's like one of those rings or something. So I'm going to say C for that. Okay, the structure of this is shown below. The reason that beta carotene is orange is that the molecule has, oh goodness, okay, 2 6-membered rings, 11 conjugated bonds. Okay, and it absorbs at the, okay, now if it's orange, now the reason why the grass outside is green is because that's reflecting green light at me, and it's absorbing all the other wavelengths of light. So if something's white, it's because it's reflecting everything. So the reason that something's orange is because it's absorbing orange. No, sorry. It's reflecting orange. Reflecting orange. And if it's reflecting orange, then it will be absorbing. So the options I have are red and blue. So I would say that it would be reflecting red, and absorbing the blue. And that's why it's appearing orange. So the answer options would be B or C. 2 6-membered rings. That's true. 1, 2, 3, 4, 5, 6, yeah. A set of 11 conjugated bonds, which are double bonds, alternating double or multiple and single bonds. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's also true. So it's, I mean, just because the question's about, so it's basically saying, well, it's saying why is it absorbing that? And it will be because it has conjugated bonds, I think. I don't think it's because it has 6-membered rings, because it hasn't said anything about 6-membered rings changing the absorption. Like if we look at the azobenzene in the previous one, that also has 6-membered rings, but that's not the reason it has a certain wavelength of absorption. It's because it has all those double bonds. So I would say that the answer here is C, because it absorbs the blue end of the visible spectrum. Okay. Phenolphthalein is an acid-base indicator, and it has different structures at different pH values, represented as 1 and 2 below. So it's either colorless or pink, depending on the pH of the solution. So, okay, so low or high pH. So if I'm looking at the differences, 1 has more hydrogen and 2 has more negative charge. So I would say that 1 is the one at low pH, because low pH means higher acidity. And if there's more acid floating around, like if I'm in a pool of acid, it's going to start donating hydrogen onto me. That's going to hurt a lot. But that's what's basically happened to that one there, is it has accepted that hydrogen on. So this is the one at low pH. So that means it's either A or C. Now, which one is colorless? So if it's colorless, it's absorbing everything, I think. And if it's pink, then it's reflecting pink. I'm not sure how to take that yet. Okay, although most organic compounds appear white or colorless, now that's actually something I should have read for the previous question, because most organic compounds appear white or colorless. So those 2 6-membered rings, they would be colorless. It's actually the bonds that would change them. So the only reason it would absorb that is because of the conjugated bonds. So that's actually probably the evidence that I should have been looking for. Anyway, it's saying they're white or colorless, but when they have conjugated bonds, then they will absorb some color. So basically it's saying which one has more conjugated bonds. So I think this is saying the more conjugated bonds will be the pink one, because as you get the conjugated bonds, it changes color. So if I count these bonds, we've got 1, 2, 3, 4, 5, 6. Is that one? Yep, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I count that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. What am I doing? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I just counted 10 over there as well. One of them has to have more. Has to have more. Hang on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Any other ones? Oh, it's very sneaky. So in the second, so they both have 10. So I was counting all the bonds in like the rings, which have like the double bonds like that. But in number 2, molecule number 2, it's got this COO group. Now COO, that represents double bond. So there's actually a double bond there, but they haven't written it as a structural form. So that means you can't see it. Which is, yeah, a bit cheeky. So that's another conjugated double bond. So that number 2 has 11, number 1 has 10. So gosh. So yeah, so 2 is going to be pink. But 2 is also the one at high pH. More double negatives here, confusing. So high pH meaning low acidity. So high pH and pink. So 1 is the structure at low pH and is colorless, which is A. Yep. Yep. Okay. Cool. 44 to 48. Okay, some kind of fungus. Consider 2 genes on the same chromosome, so do not consider recombination for 44 to 46. So consider 2 genes on the same chromosome, each with 2 alleles, AA and BB. One octad has the following order. Which of the following could be the genotype of the diploid myocyte? Okay, so 2 genes on the same chromosome with 2 alleles. So what is an octad? So an octad is just a bunch of different spores. So for just one of its pairs, total of 8 haploid things are formed. So I'm not sure where that other thing is coming from, but figure 1 shows one resulting from the diploid myocyte genotype AA with respect to... Okay, I see now. So it's saying that basically, so it's told me that we have AA, and basically we copy both of those. So we're going to have 2 times A and then 2 times A. And then these are going to split into A and A, into A and A. And then these are going to split again. And then that gives me all of my, that gives me my octad, or whatever. So it's told me in the octad, I've got AB, 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 AB. Well, they're all the same. Now, this is telling me that basically, like if you look at it, I think it's literally just like all of these are identical to this, and all of these are identical to this, and this is there, and this is there. So the first 4, and these are all identical as well. The whole first 4 are identical. The whole second 4 are identical. So the genotype should be AB. Well, I need to combine these. So it'll be the 2 things that we've had. Like this is the thing on the top, if you imagine that. And then the second set of 4 is all A big B. So that will be the thing on the bottom. So that means my genotype should be this. That could be the genotype, and I think it is. So that's A. All right. 45. A diploid myocyte is heterozygous for gene A. Consider the possible genotypes for gene A in the ACER that are listed below. Which one of 1 to 4 could have been produced from this? So it's heterozygous for A, which is basically what we've got here. So you could definitely get 1. You could, I don't see why you couldn't get 2. I mean, that's the same thing, just in reverse. Okay, so all of them are technically possible. So why would they have a different order? So something about this ASCII, I think, is important. the two pre-spores formed in the first could be reversed. Okay, so it's saying that this order could be changed, this order could be changed, or this order could be changed. But these ones here I don't think particularly matter because they're going to be identical anyway. So it's saying that I think it's only 1 and 2 because I don't see. So it's saying that for each one of these we duplicate this, and that could actually be here as well. That big A could be there, but those two A's have to be together. We can't have big A with little a. I'm hoping that makes sense. We can't have this up here because when we do that first division, that first replication, we're just replicating each of those alleles separately. So the only way we could change the order is it says this can be flipped, but we can't get, because I'll draw out the thing again. So we've got the example they gave us is big A, little a, and then it says that it replicates the big A and the little a, and then these things, one goes up here, one goes down here, and this order could be flipped. But either way, we've replicated these two together. So to get any of the combinations in 3 and 4, we would need to have flipped, we would need to have somehow swapped this with this or something, which isn't possible. And 4, could we have got 4? I don't think we can get 4 because 4 is like big A, little a, little a. But once we're down that tree, like once we've got those A's, these can switch together, but they can't switch with the other half as far as I can see. They're done. They're off in their different paths. So I think the answer to this one is A, 1 and 2 only. Okay, 46. That's getting messy. 46. Consider the diploid myocyte shown in figure 2, in which gene A and B are located on non-homologous chromosomes. Okay. Which of the following lists the only possible genotypes in the pre-spores after the first meiotic division? Non-homologous chromosomes. So what does that mean? I don't think that matters. I think that's just irrelevant information. So only possible genotypes in the pre-spores after the first meiotic division. So basically, we've got AA, AA, BB, BB. And these are after it's split. So these are basically the things that are coming in at this stage when they've already divided. So one of them after the first meiotic division. So this could go here, and this order doesn't particularly matter. These have to get split, and these have to get split. But we don't really know. But that could be either direction. This could go here or this could go here. So I'm going to leave the B's for a second. It's just going to be mirrored anyway. So it's just going to be AA and AA, and either the B is going to come here or the B is going to go here. So it's either going to be all big or it's going to be that, or the other combination. Well, that's one thing, or this one goes here and or that one goes there. So that's, we could get that as well. And then after the division, we're just going to times 2 all of these things, I think. So I don't think it particularly, we're just going to duplicate whatever's together. So I think the only combinations are So I think that's A. I think. Unless I've got something wrong. I've also just done 3 A's in a row, which is very scary. I think it's A because you're either the A, if we look at the figure, the A's split and then they stay there. So if we say that the B's do the same, those B pairs are going to be together, and either one's going to go up to the top with the big A's or it's going to go to the bottom with the little A's. But we're not going to be able to get a big B and a little b. I don't think. Yeah, no, I don't think so. Okay. Oh no, it keeps going. I don't like this question. The spore order in the ACER presented above is AAA. Which of the following is not another possible spore order? So this is just saying that there's some kind of recombination going on. Okay. Which just means it changes what's possible. So when does that happen? Crossover during the first division of meiosis. Okay, so so it's basically saying we get AA and AA instead. And then we're going to get 2 of them, or they're going to split up, and then they're going to double. Now, the way I'm interpreting this is they're going to double, so we're going to have 2 big A's or 2 little A's together in a row, but this it said that these can swap orders. So they've given us the order AA, 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 AA. I don't know why I keep saying that. Anyway, they've given us that order, which is what basically I've written down here. If we just times all of this by 2, that's what we've got. So another possible order is if they didn't switch, which would be, no, well, that's actually what's happened. So if they did switch, you could have little a, big A, big A. And then this one could just stay the same. So that's another possible combination. Or these could also switch. So this combination that I just drew is C. So C is possible, I think. So that's incorrect. I think B would be possible as well. I think, yeah, A would be possible as well. And I don't think D would be possible. Because D would be they would be coming back together in some way. Okay, nearly done with this question, thank God. 48. Consider a crossover between these genes. Which of the following is not a possible spore order? Oh, man. This is tough. Consider a crossover event. What the hell is in, like, how does that work? So it's saying that the thing at the top, when we have that little diagram thing, the little arrow thing, it's like the 2 in the, it's the 2 in the middle, which, because we've got this thing like this. So I'm interpreting that because it's kind of color coded. So you can see that the bottom once we've done this division, if this was blue, we end up with that blue thing here. It's still got the blue thing, but we get this little bit of red here. So I think the things on the outside stay the same. That's how I'm interpreting that. The things on the outside stay the same. The things on the middle switch. So if we look at our picture, we've got this. This. So these are going to switch over. So that was kind of useless. Didn't really matter that much. So which of the following is not possible resulting from this recombination event? So that happens. So that means that we end up with this and this. Now, these things just go off. Yeah. And then they split. And then we double. But there can also be some swapping around in here. So I think I've done that wrong. No, so these things double. Yeah, no, that's all right. So that I've mixed it up slightly, but basically these things are going to come off. Oops. These are the things which will double. So you're going to get AB, AB. And so you're going to get two of these things in each. But I think that these orders could be changed as well, I think. So which of the following is not possible? So basically, I think what we need to look for is these four, but not in any particular order. So I think you can't have A. Now, if I get something wrong here. Yeah, I might have got something mixed up. This is one I'd totally skip if I had this in the exam. Now, I didn't think it would be possible to get all these heterozygous ones, but all of the options, by heterozygous I mean like two capitals, or like one capital with one lowercase, but all of these actually have that as an option. So I've clearly misinterpreted something. So I would say that I need to go back to the drawing board and I need to say, okay, they don't switch. So I need to get the recombination down better. So it's actually, if I go by this color scheme thing, it's actually like that. So the only thing which changes is going to be this letter here. So actually, scribble all this out. So the only thing which is actually going to change is these two letters in here. So these ones are going to switch. So these ones, so this is going to become this, and this is going to become this. Now, what happens then? We basically separate these two genes. So we've got A, B, AB, AB, AB. Goodness gracious. And then yeah, and then I think these times by 2. Oops. Gosh, this is, yeah, not something that I'd be spending my time on exam day. So we basically are looking for sets of 4 in a row like that. So A has that. Yep. So A is good. B is also good. C is good as well. So it better be D. A, B. Yeah. D doesn't fit with mine. It's got these ones. It's got this combination with this combination, which I think by my logic doesn't work. So I'd say 48 is D. Now that was a really long question. All right. Cool. These 2 questions I do know, but we'll go through them anyway. I really like them as questions. So this one's got a triangle and it says that you put equal amounts into, you've got the total amount. You've got this triangle and it basically says the ratios of how much is in each of the 3 points. So it says this one is 15 to 40. Okay, and then these ones we don't know. And it says total equals 2.3. And then the amount in 2, which is, so 2 is down here, 1's here, 3's here. It says the amount in 2 is 1.2. So there's 1.2 over here. So the way I think about this question is if there's 1.2 over there, that means there's 1.1 everywhere else. So we've basically got 1.1 into these 2 here. Now, with ratios, there's a number of different ways to do it, but I like to think there's 50 for every 40. So I like to actually combine ratios to end up being a total. So I would say that there's actually, if you had 65 things, 15 go over there. 55 things. If you had 55 things, 15 will go over there and 40 will go over there. So really, number 1 gets 15 over 55 and number 3 gets 40 over 55 as a percentage. So I'll just simplify that as just 1 over 5, I think. That'll do. And then 4 over 5. So if we have 4 over 5, and I'm just going to say that instead of 1.1, it's just 1. So we'd have 0.8 over here, because we've got 4/5 of 1 there. And then we've got 1/5 over here, which is 0.2. So I would say that 1 has 0.2, 2 has 1.2, which is what we got told at the start, and 3, sorry, I've done those in different formats, is 0.8. So the ratios of those, because it says 1 to 2 to 3, is, might just times everything by 5. So I get a whole number. So that's 1 to 6 to 4. So the closest, so the only one that really fits here is A. So 49 is A. Now 50, this is my favorite ever question in the GAMSAT. So it says, making a few assumptions, what's the best estimate of the rate at which your fingernails grow? I use this one all the time and everyone always gets tripped up with it. They say, oh, I don't know how fast my fingernails grow. And something I like doing is actually covering up the answer options and saying, can you answer that question? If I just covered up those answers, can you tell me how fast your fingernails grow? And they say, oh, maybe like 1 or 2 millimeters a week. I'm like, okay, great. Then why don't we use that? So you do know how fast they grow. You don't know how fast they grow in meters per second, which are the units of this question. So really, this is just a maths question. And yeah, I would say like, maybe 1 millimeter per week, something like that is probably a reasonable amount. And it doesn't really matter because all those answer options are a factor of 1,000 apart. So 1 millimeter per week, and then we go through the unit conversion process. So if I remember, I'll make sure I link my video to unit conversion in here, but we just convert these to meters per second. So there's 1,000 millimeters in a meter. There's 1 week equals 7 days. 1 day is 24 hours. 1 hour is 60 minutes. 1 minute is 60 seconds. So I'll just check all that. So millimeters, millimeters, meters, weeks, weeks, days. Yep. Days, days, hours, hours, hours. 1 hour, 60 minutes. 1 minute, 60 seconds. Cool. So the only units that we're left with here is meters per second. And basically all I've done here, if you need to watch the videos, I've just done all these conversion factors just to make sure I've got the same unit. I've got the same number in these different units. So now I've just got to convert all this. So I like to just write everything out because it's been a bit messy here. So we've got 10 to the 3 here, times 7, times 24, times 60, times 60. And I like putting my units over on the other side because as you can see with my writing, that looks like a 5. So if I put my meters per second in here, sometimes I've looked at that as a 5 and ended up multiplying my answer. So just put them out of sight, out of mind. And then I like just putting everything in scientific notation just to make it easy. So to go 1 over 10 to the 3, I'm going to change that 7 to a 10, times 2 times 10 to the 1, times 6 by 10 to the 1, times 6 by 10 to the 1. My next step is always just I reorganize. So I move all the numbers to the front. It's just something I like doing. I go 2 times 6 times 6, times 10 to the 3, times 10 to the 1, times 10 to the 1, times 10 to the 1, 10 to the 1. I'm hoping I'm not, so yep, just making sure I counted all those correctly. And then I just do the math. So I just go 6 times 6, 36, times 2, 70. 10 to the 3, 4, 5, 6, 7. And then I have this other rule, which is I make the numerator bigger. So if you're missing out on if these are all new maths rules to you, but there's many ways to do this, but this is how I do it. So I like converting the top number to something that's bigger than the bottom because I find 1 divided by 70 very difficult. So I kind of change this to 10 to the 0 and then I convert it into a bigger number. So for example, I could make this 100 times 10 to the negative 2. That's the same as that. I've just converted it to another number in scientific notation. And then I'm just going to round that 70 up to 100 as well, times 10 to the 7. So they just cancel off and I get 1 times 10 to the negative 9. So that is answer option C, the 50. Okay. This question as well, unfortunately, I know, 51 and 52, I like this question quite a lot. So it's another kind of conversion pathway. And it's actually quite common. I've seen this before, is it says, which of these things would produce 13C labeled ATP? So you kind of need to interpret that as if all of these things were labeled. So how do you interpret that? You say, if they were labeled, it's like you can track them. You've got a label on your package or something like that. You can track where it's going. So it's basically just saying, it's just that reasoning stuff. If you can track these things, which one will produce ATP, And if you look at all the arrows with ATP, they're actually all just coming off like this. So all of the other things have these separate arrows, like the NADs over here, the glucose is over here, and it goes through to pyruvate. And you can look at all these things, but none of these things actually go into ATP. ATP is just involved in those reactions. So none of these would actually result in the production of labeled ATP. So that one's D. And then if I go on to the next one, so again, I do know the answer to this because I've used it before. It's quite tricky, but it said how many moles of ethanol are needed to produce as much ATP as 1 mole of glucose. So a lot of people just count, they can track the ATP in the conversion sequence, but they miss the little thing in the bottom left, which is something that I think you need to just make a little bit of a leap of faith and just say, why is that there? So how can I get ATP? Well, I can get ATP through the cycle, like from glucose to pyruvate, but I also can get ATP if I convert NADH back to NAD+. That actually makes 3 ATP. And as you can see in the conversion pathway, you're making a lot of NADH. So how I would set this out is 1 NADH equals 3 ATP. So I would say for 1 mole of ethanol, for example, we would maybe do it like this, something ATP and then total, something like that. And we'll do ethanol. I can't write, it's disgusting. So we've got 1 NADH, 2 NADH, 1 ATP, 3 more NADH. Now each NADH is 3 ATP, so this would be 16 ATP in total. Now I'm going to do half a mole of glucose. Per half mole of glucose, we're going to get 1 NADH, 2 ATP, 2 NADH, then we're going to do 1 more ATP, and then we're going to get 3 NADH. That's half a mole. So this is going to be our 15, 18, and then we're going to double that to 36. So to get the same ATP as 1 mole of glucose, which is 36, we need to double that. Well, we need to between double and triple. So the answer here will be C, which is more than 2 but less than 4. Now, just I think, the takeaways from that, which is answer C, the takeaways from that are to just think really broadly about what could actually, cause that to produce ATP, but also you would get an answer option that just doesn't seem right, and you probably would have seen that a few times today. I've been like, it doesn't seem right, it doesn't seem like it's lining up. And you can go back and almost use the answers to help you reverse engineer what might be the case. And then when you get an answer option that looks good, then you're like, yeah, that's it. So it's taking a little bit longer than I thought. So I had a little drink of water, had a quick break. But yeah, we'll move on to questions 53 to 57. So 53 says, a major distinction between the two models is that. And again, I'm going to kind of take an approach that I took earlier and summarize the answer options. So it's kind of saying glycoproteins are modified in different ways. Glycoproteins move between cystine A, whatever that is. Vesicles move between cystine A, and then vesicles are involved. So it's kind of talking about glycoproteins, the movement, vesicles, all that. So glycoproteins. So what have we got here? So figure 1 and 2 summarize 2 models proposed to account for the passage of glycoproteins through the Golgi. Figure 1 is that cisterna are formed in coalescing vesicles, and then it progresses through. It kind of starts here, goes through, and as it goes through, it's modified. Okay, cool. In number 2, it says the glycoprotein, so it's basically the same up to here, because we've got all this other stuff going on, but it's saying that it's the same up to here, and then these things like bud off and join the next. But they're also modified in this process. So as far as I can tell, I don't think they're modified in different ways. The glycoproteins move between cystin A in 1 but not 2. That's not true. I think they move between in both. Vesicles move between cystin A in 2 but not 1. Vesicles are involved in 2 but not 1. I think there's still vesicles in 1. The cystin progresses from one end of the Golgi stack. Yeah, no, so I think in the first model, it's kind of saying that the vesicle forms, it's almost like it forms with the Golgi stack, and then as it progresses, it modifies, and then it breaks into vesicles. Whereas in number 2, it's saying that the vesicles kind of come off the stack. So there's like this stack here, and it's like it the vesicle either bonds with it, and then the glycoprotein moves through, and then it becomes a vesicle again, or the vesicle bonds, and then it kind of jumps between, becoming a vesicle every time. That's how I'm simplifying it. So I would say the answer is C. Vesicles move between the cystin A and 2, but not 1. Okay. 54. Instructions come from organelle Y to organelle X that lead to the production of protein. The instructions carried from organelle Y to X are in the form of DNA, ribosomes, transfer RNA, or messenger RNAs. This just seems like a bit of basic cell biology. Before the Golgi would be the ribosomes, and the ribosomes take mRNA. So we make DNA into RNA, and then that goes to the ribosomes. And then we make the proteins. Now we're talking about the Golgi, so I think it's good to have a basic understanding of all these aspects of cell biology. To me, it looks like Y is the nucleus, and then X would be the ribosomes, especially considering that's between the Golgi and something. So I would say that this one would be D, 54. 55, which of the intermediate substances contains galactose? So it says that we go from 2 GLCN AC whatevers to 4. Yeah. And then it says we go from 8 mannose to 3. And we go from 0 galactose to 2. We go from 0 salicylic acid to 2. So that's what we know. This is like the start thing, which is G, and then this is the end protein, which is U. So if we look at all these steps, we can kind of infer what the things are doing. So mannosidase, well, considering we're losing we're losing mannose by the end of it, I would say that the mannose takes away mannose. Then the GLC whatever transferase, I'd say that transfers some GLC groups because we increase the number. Then again, GAL transferases. So it seems like transferases are adding on and the oxidases are taking away the mannose. So I would say that the GAL transferases are the ones that give us the galactose. And we don't get that until the GAL transferase hasn't done anything until T. So the only ones which will have the galactose groups will be T and U. And it's only saying intermediate, so it'll be only T. So that's A. All right. So the enzyme whose activity is greatest in tube 7, the enzymes whose activity is greatest in tube 7 is probably so in tube 7, the greatest one is the mannosidases and the GLC transferases. So the activity of those is to remove mannose and add GLC NAC, so that's A. That's what we kind of just discussed there. And then which of the following is most likely? So what's this? Cis-cystine A, medial trans-cystine A. So I kind of read those before. So the cis-cystine A are basically it says the modification. If we go back up to the diagram, it says that they bond here. This is the cis-cystine A, this is the medial, and then when they butt off again, this is the trans-cystine A. So it says that the modification process happens as it moves through. Whichever way it moves through, that's just when it happens, when it's moving through the Golgi. So in the medial cystine A, that's when things would be getting modified. Trans would be completely modified, and cis would be they're not modified at all. So if we look at those options, it's saying in tube number 9, cis-cystine A predominate. No, because that's when the GAL and SA transferases are most active, which is towards the end. So it's not A. In tube number 9, medial cystine A predominate. I don't know about medial, because they seem like they're done. Oh, especially in tube 9. Yeah, I was looking at the whole thing. Like tube 9, they're almost all done. In tube 7, trans predominate? No, because tube 7 is when, like, we're middle of the pack, basically. So I think this will be D. The medial cystine A predominate. So 57 will be D. Okay. 5861. So C4C32 represents which of the following structures? So ciphers are alphanumeric strings that we use to represent structures. So I like the look of the first one because that's probably the most similar to what I have. A 4-carbon chain with a 1-carbon chain attached to the second carbon atom. So we've got C, C, C. So this number is the length of the chain. This is the length of the side chain. Oh, that's not a C, sorry. And this number is the carbon which it is attached. Something like that. Cool. So if we've got C4, we've got C4C3, 2, we've got a 4-carbon chain with a 3-carbon chain attached to the second carbon atom. So it'll be 1, 2, 3, 4. Oops, that's 5. And then on the second one, we've got a 3 carbon chain. 1, 2, 3, 1, 2, 3. So I think that's D. It's slightly different to what I drew. 1, 2, 3, 4. Okay, 1, 2, 3, 4. Yep. 1, 2, 3. Yep. So D for this one. 58D. 59. C2. Okay, so now we've got this other thing. So this says that it's a 4. So again, we've got that C, which tells us the number of carbon chains. But then it's got A3, C112. So a 1-methyl cyclopropyl group attached to the second 1-methyl. So it's kind of shown me. Okay, so really, so they've just given me a confusing name. So the A3, this is A. So this number here is the number of carbons. Is it still on the screen? Yeah. Number of carbons in ring. And this tells me this is the same thing, the length of the side chain, and then the carbon to which it's attached. So it's very, very similar. So this is saying C2, so that's a 2-carbon chain. And that's what they've got. Three-carbon alkyl ring with a 1-carbon chain attached to the first carbon atom. Yep. And then that's a 4-carbon alkyl chain with a 1-methyl cyclopropyl group attached to the second carbon atom. Yeah, okay. So we've got C2, so that's a 2-carbon chain. On the first carbon, obviously, we've got a 3-carbon ring, but we've also got a 3-carbon side chain attached to the first. So I'm actually going to do these separately. It's 1, 2, 3. 1, 2, 1, 2, 3. And there's my 1, 2, 3. And then that should be attached, I think, to a 2-carbon chain like this. I think. It's a bit frightening because why are all these in the middle? So that methyl 1-carbon chain, so that's the length. So it's 1. Yeah, that's 1, 2, 3. Yeah. So it seems like when you attach it, there's an extra group, because when we have the whole thing together, it says there's a 4-carbon chain, and then it says there's a 3-carbon triangle, which I can see, with the 1-carbon group extra, but there's another extra connection. So I think we need to have a 2-carbon chain, then attached to the first carbon we have our connection, then we have our 3-carbon triangle, and then we have somewhere, I assume it's going to be on the same thing, we have a 1, 2, 3-carbon side chain. So something like that is what I want. Which is C. So 59 is C. All right, the structure of which of the following has the lowest molecular weight? So C5, C. So basically, I just need to count the number of carbons. Now, that first number refers to the length of the chain. Then all the subsequent C's are the length of the side chains. So I can just add up all those numbers. So we got 5, 6, 7, 8. And each of the A's is also a carbon, plus 1, actually, because there's a connecting, like this one here was the one that we just drew was C2, A3, C3. So really that should be 8. But if you look at it, we've got 1, 2, 3, 4, 5, 6. I thought it was 9. Should have been 9. It's just the bond. Okay. So it's not an extra carbon, it's just an extra thing. So has the lowest molecular weight. So these all have 8. So why 5, 6, 7. Okay, they all have 8. But that's just the carbons. So there are the hydrogen as well. So I'm just going to do a small scale test just to see. So this carbon is CH2. These are all CH2s. So that's C3H6. Now I think that's going to be lower than if I just had 3 in a chain, because this is CH3, CH2, CH3. So that's C3H8. So now what if I had that branched off? So what if that was like C2 and then a side chain? Wait, hang on, no. That won't work. I'll need to go up. So let's say I've got 4. CH3, CH2, CH2, CH3. So that's C4, H6, H8, H10. Whereas if I did a branched one, 1, 2, 3, and a branch, that's still a CH3, that's a CH3, that's a CH3, and that's a CH. Yes, so that's still C4H10. So it doesn't matter, the branching doesn't matter. So what I'm trying to figure out is, because they all have the same number of carbon atoms, I think, which one has the least amount of hydrogen? Now, I think that the ones with the branching of it doesn't matter. They'll still have the same number of hydrogens, but as I've seen here, if you have that triangle structure, that will reduce the number of hydrogen atoms. So I think 60 is B, because that's the only one with that in there. And then 61, how many hydrogen atoms are in the structure with the cipher A5? Now I'm gonna do a little cheeky. These will all be CH2s, right? So that's going to be, basically we can just double the hydrogen. But there's that connector as well. So this is, so I think there's like n, 2n plus 2 is the formula to get from here to here. So I'm just trying to cut down the amount of work that I need to do. So if I've noticed a pattern that if I just double the number of carbons in a triangle thing, or whatever it's called, that will give me the number of hydrogens. And then to do that in a straight chain or a branched chain, I need to double it and then add 2. Now, my only thing then is just what will happen if I like connected these 2 chains, for example, there's actually 14 hydrogen, but I'd have to lose 2 to make them fit. So I think this is a faster way slightly. So I've got A5. So that means there's 10 hydrogen there. I've got C1, C3, and C5. So I think that's the total number of carbon atoms. So that's 9. And I need to double it and add 2, which equals 20 hydrogen. Then I need to add these together, which is 30 hydrogen, but then I need to minus 2, I think. 28 hydrogen, which is answer B. Now I hope that's right. I really hope that's right. I think it is. That's the total number. There's 6 there. There's definitely 8 there. And if I join them up, which these are joined, they have to be joined, I lose 2. So it's 28. I'll lock in B. Okay, 62 and 63. I've done this one as well, actually, which is a shame, but I think it's a good question. I don't completely remember it. So it's a classic, like really complicated graph, multi-dimensional, and I think it's just about looking at variables in isolation. So it gives me a bird of mass 2 kilograms is soaring a circular path. The speed is this. The angle of bank is this. So if it halves its radius, increase its angle of bank, what's the best estimate of the new speed? So I would just say, okay, well, I'm starting at 12. So we've kind of got this graph where we've got all these lines going this way and all these lines going up this way as well. That's the angle of the bank. And then we've got the time and also the speed. So I would just take 1 point. So it's told us the speed's 12, so I'd just go across this way. And then it's also told us the angle of bank is 25 degrees. So we can go here, find the intersection point. And then if we follow that up this way, so remember each of these, it's just about finding the angle. It's very similar to this question, which is like a triangle. It's like a phased quaternary diagram or something like that. But a lot of people really struggle with that one. I think it's just because there's so many dimensions. It's really just about which way do you read the graph. So if you look at the radius, all the numbers for the radius, if I do them in red here, it's all like here. It's all 2, 4, 6, 8, 10. So it's about reading that this is the radius going this way. And then the angle of bank is, these green lines going up this way. And then you've also got the speed going horizontally, and you've got the time going vertically as well. So it's quite complicated, but it's just about reading which way to read each variable on the graph. So we have 12, angle of bank 25, which gives me a radius of 32. Now it says that I halve the radius. I think was it 12? 12, angle of bank is 25. Angle of bank 25, 12, yep, 32. So it halves the radius, so it's now 16, the new radius, and increases its angle of bank by 10 degrees. So basically I've gone from like 32, which was over here somewhere, all the way down to 16. And this isn't, these numbers aren't adding up because I've just roughly done it, but 16's around here if you look on the graph in the table. And now that is the new thing that we're looking at. And we've gone from 25, which was here, we've increased it 10 degrees, which is 35, which is now like here. So we can find where these intersect and then that will tell us the new speed, which is what it's asking for. So if I do that 16 and 35, that corresponds to a speed of a bit over 10. So the answer will be 10. So 62D. 63, so now it's given us a bird of mass, blah, blah, blah. Fine with that. What does it want? The angle of bank at which the bird is soaring. So what do I need? I need the angle of bank. I can get that from the radius, which I've got. So, but I need another variable. So I need the speed, which I can get through that formula, or the time, but I don't have the time. So, so now we can use that formula. Force equals mv squared over r. Force also equals mass times acceleration. It's always just good to think, how am I getting these variables? So it's told me that the bird is 2.5 kilograms, gravity is 10, so that force will be 25. So 25 equals 2.5 times v squared over 10. So basically, times by 10, 250, divide by 2.5, divide by 2.5, 100 equals v squared. So therefore v will equal 10. So now it's told me that the, what was it? The radius is 10 and the speed is also 10. So I think that gives me an angle of bank of 45 degrees, which is D. Cool. 63D. I've done all that right. It's just weird that all these 10s have come out, but that looks right. It's given me, that's force, that's velocity. The radius wouldn't have changed. 10, 10, yep. No, happy with that? Cool. All right. Scary looking one. Okay, the figures below show the separations of a mixture using solvent 1, then solvent 2 left, and using solvent 1, then solvent 3 right. Which of the following would be produced by separating the same mixture using solvent 2, then solvent 3? So what have we got here? So basically, so it's talking about chromatography. So it separates that. Okay, and then you rotate and it moves it another direction. So it's kind of like you put in a solvent, it moves it up, and then you put in another solvent, and then it moves it the other direction. That's how I'm interpreting it. Because you move the piece of paper or something. I don't think I'm going to look at that. Okay, so it's saying, so basically on the left one, we've used solvent 1, then solvent 2. Why has it got 2 dots though? Oh, because you got 2 things in there. Okay, so if I look at these 2 things, they've both gone through solvent 1 first. So if I look at what's similar, I've got like a dot here and a dot here, and then I've got a dot here and a dot here. Now they both had solvent 1 first. This is the starting point here. So I would say that solvent 1 increases it this distance. So basically after solvent 1, they would both be like this. So then solvent 2 has moved them from here to here. That one's like bugger all. And solvent 3 has moved them to these positions. So it's gone to like here, so not as far, but then this one's gone further. So if we did solvent 2, then solvent 3, we would get, so now we've got to kind of combine these. So we would get a big movement of this dot. So they would all start here. And then we send solvent 2. So this one's going to go all the way up to the top. And then this other dot's not really going to move at all. So see how this is the same thing as what I've drawn on this. So basically I've done solvent 1. So because both of these have gone up the same height and they both had solvent 1 first, I can say that that's the effect of solvent 1. So after solvent 1, we're going to get this picture here where they've gone up that distance. So that distance that I've done here is the same as this distance, which I've figured out from those graphs. So that's what's going to happen after solvent 1. And then from that, we can then see where they end up to work out how far solvent 2 and 3 take them. So now that I know how far solvent 2 take them, they're starting here, and then I've just extrapolated these movements in red for here. Now, those things are going to move the green distance to the right. So that's quite a long way. It's about like 2/3 of the way across to there for this dot. And this dot moves a fairly long way away as well, but not as far. It's to like here or something. So what we would have is, that picture. I don't know if I'll scribble them out. So that's what we would end up with, which looks like option C or B? B. Yeah, B. 65. So the figures below show the separations of a mixture using solvent 1, then 2 on the left, and then solvent 1 and 3 on the right. Is that what we just had? Maybe different solvents or something. Oh, different mixture. Okay. Which of the following lists solvents in order of increasing polarity? So it says that a more polar solvent, more polar, more movement. So we can see that this is the same mixture. So we've got 1, then 2. So if we look at both of them, again, same process, we've ended up with 2, it's like 1 here, 1 here, 1 here, 1 here. So this is 1, then 2. This is 1, then 3. So 1, if we make that blue again, is going to be the first movement up, which is like this, which is like nothing. That looks like the least by far. 2 is then going to be this distance, which is not very much. And then 3 is going to be this distance. So same logic as before. So 3 will be the most, then 2, and then 1. Yeah. So 3 over 2 over 1. Now this is increasing polarity. So that's basically saying the lowest one will be first, and then it's increasing. So this will actually be answer option A for 65. Okay. So 66. So to prolong platelet lifespan in blood banks, which of the following is most readily achievable and useful? Okay, so decrease the rate of transcription of BAC, MRA, increase the rate of transcription of BCL-X, and that's in mature platelets, administer ABT737 QVD. Okay, so I'm going to have to do some reading here. So it is, okay, so it's been found that, so it's saying BCLX increases platelet survival. Now, the thing that I'm noting is that it does say in mature platelets. I kind of think, is that useful? Like, if they're probably already dying, or maybe, I don't know. We'll see. Anyway, it's something I'm thinking about. Now, the protein's effect is countered by, so I'm going to start drawing a little diagram here, countered by the drug ABT737. BAC induces platelet death. So BAC induces platelet death by affecting caspase 3. So BAC leads to death by activating caspase 3, and then BCL binds BAC, inhibiting the function. Okay, so BCL binds BAC, BCL inhibits BAC. And what's this other one? QVD. QVD inhibits caspase 3. So then we've also got this other one, QVD. I've got all those around the wrong way. Okay, so which one would be most readily achievable and useful? Decrease the rate of transcription of BAC in mature platelets, increase the rate of transcription in BCL, mature platelets, administer. I think it would be more achievable and useful to just give the thing which stops the death happening. So rather than bugger around with all these, that seems like the most direct way to affect that. So I think all of these options except for C are correct. But I think that, changing the rate of transcription of a protein, I don't think would have, I think it'd just be easier just to stop the thing that's actually killing them in a way. So I'd say D for this one, for 66. 67, in general, the percentage of platelets produced on a day to be reduced to just less. In general, for the percentage of platelets produced on a day to be reduced to just less than 5% by the 10th day after production, the half-life of the surviving platelets must be closest to. So it's just saying after 10, I've seen a few of these half-life questions. After 10 days, we need to have just less than 5% remaining. That's how I'm interpreting this. So we would, every half-life, this is how I like doing these half-life questions, we just halve the number that we have. So we go from 100 to 50 to 25, 12.5 to 6.75, whatever, and then to 3, whatever. So this is 1, 2, 3, 4. We need to go through more than 4, but less than 5 half-lives. So for 10 days, so we need this 4 to 5 half-lives to be equal to 10 days, which means that one half-life, I think, would have to be 2 days. If it was 3, we wouldn't be getting there, because at 4 half-lives, we would have done 12 days already. So the only one which works here is B, which is 2 days. Okay. Which of the following is most strongly supported by figure 1b? So BAX has more of an effect than BCL. BAX has more effect than BAC. BAX has no effect. So it's about BAX, BCL, and BAC. Another classic one where all the things are very closely related, obviously. So if you look at figure 1b, we've basically got I'm seeing all these, it's telling me the half-life of these platelets. So I've got all these graphs telling me the half-lives, and it's telling me all these different variations of BCL back and backs. So if I want to determine the effect of just one of these genes, I need to make sure everything else is constant. And this is a really common thing to do when you're analyzing graphs, is keep everything constant. So I know I need to look at all of them. So what I might look at first is analyzing the effect of changing BCLX. So we'll just start with the first one. So what I need to do, what I might do, for example, is I might compare columns 3 and columns 5. So if you look at that, we've got BCLX, back, and backs. So BCLX, in column 3, we've got plus, 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 plus for everything. Plus, minus, plus, 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 plus. So the only thing which has changed is changing this BCLX thing to the non-mutant or whatever, the deactivating mutant, which is what it says there. So the change there cannot be due to anything else other than BCLX, and that's why you want to look at them together. So if I look at column 3, that half-life is about 2, and then it goes down to maybe 1 point something, maybe 1.2, we'll say. So I'm going to put in the back of my mind here, BCLX equals negative 1, I'll just say, half-life. Now it wants backs. So backs. So what am I going to look at for backs? I'm going to compare, same logic here, I'm going to compare backs. Now there's only one column where backs actually changes, which is between columns 1 and 2. Backs goes from a plus minus to a plus plus. Well, you could compare it with any of the other ones, but the reason I'm doing 1 and 2, is because that's the only pair of columns where these don't change. So you could compare backs in 1 with 2, 3, 4, 5, but you're going to be introducing all this other variability. So by looking at 1 and 2 together, we're just seeing the effect of changing backs. And I can see that it goes from like a little bit over 3 to a little bit under 3. So that's probably about like roughly 1 half-life as well. Okay, and then we need, the last one we need is back. So back, I might look at, I'll look at 2 and 3, I think. 2 and 3, back goes from that, ignore that little red line there, goes from, that's all we're changing. We're only changing the back. And we can see that back goes from like 2.7 to 2, something like that. So it looks less than 1. It's definitely less than 1. So it's not backs. Sorry, it's not back. Oh, it's less than 1, I would say. Half-life. So I might have to get a little bit more granular here. So I can rule out, so backs has less of an effect. So let's just look at these options. Backs has more effect on platelet half-life than BCLX. I can't quite conclude that. Backs has more of an effect than back. Yes, I would say that. Backs has no observable effect, and that's wrong. Backs has less effect on half-life than BCLX and back. No, that's also wrong. So I think the one that's most supported is that BACS has more of an effect than BAC, which is B. And 69, so in explaining the lifespan of a platelet, which of the following is most consistent with the information presented? The number of BAC molecules in a platelet increases over time. Let's go back up to my little diagram. The number of BAC molecules increases over time. So, well, I mean, more die, so I think that's probably supported. Does half-life, how does half-life change? I'll think about that one. The effect of BAC on caspase 3 decreases over time. That's wrong, because if we had less caspase 3, caspase is saying there's less activation of caspase 3, which would lead to longer survival. Levels of unbound BAC increase over time. Now, BAC binds to caspase 3 to activate it. So, no. The amount of unbound BAC will decrease over time because I think more of it's binding to caspase 3. Caspase 3 activity decrease over time, also incorrect. So I think the answer here will be A. The number of BAC molecules in a platelet increases over time, because that's the only one which increases. Yeah, cool. All right. Okay, so funnily enough, the triangle graph that I was talking about earlier is actually questions 70 to 72, so I do know this one. But again, we've just got this triangular graph, and I think it looks really scary because you haven't seen many graphs like this, but it's all about just reading the axes for how you read these graphs. So it's got one thing on the side, and if you look at the axis ticks, it's got them being read in this direction. The tyloxapole on the bottom is this direction here, and then the doc on this one is down in this direction. And you can actually take one of the points, and because it will tell you that, this thing has this amount or something like that, and you can just verify that the way you're reading the graph is correct. But let's say this was like 20, 30, 40 or something like that, you can verify that on the graph. So that's how you read these graphs. But let's just go through the questions. So it said formulation P has 15% tyloxapole and 15 tylo. Q has 30% tylo. Which is true? So if we look at the tyloxapole, we read it in this direction. So P, there's a region, it's like this kind of line here, and that corresponds with a region here, and also like another region here, it looks. So it could be Z or Y, which is micro. Z equals micro, and Y equals nano. Now for Q, that's the same thing. So it's the same kind, it's a 30% line, it's a little bit higher up, but it could also be in Z or Y. So they could both be microemulsions, which is C for that one. Okay. 71, formulations containing at least 40% DOC. So again, I'll just get a little graph for us. So 40% DOC. DOC we read this way. 40% is like the line here. The only region that would cross over with is X, and X is a macro emulsion. So they can only be macro emulsions, which is B. And then 22, which of the following is closest to the maximum proportion of DOC that could form a microemulsion. So a microemulsion is region Z, which is kind of around here, and it wants the maximum amount of DOC. And again, we're reading it in this way. So we want the number that kind of corresponds with the very edge of that microemulsion zone. And that would be around 30%, which is answer option B. Okay, on the home stretch now. 73. 2 6-base fragments obtained from a single 12-base DNA sequence are AT, TGAT, and ATA, TTG. So the 2 fragments represent at least. Okay, so it's telling us that there's one 12-base fragment. So that's like just 12 letters. Yeah. I don't need to draw that out. So there's 12 letters just in a DNA sequence, and they've given us 2. Now, they've given us 2 6-base sequences. Now, how I'm thinking about this is they could have given us this 6 and this 6, and that would make up all 12. That's a possibility, but it's saying they represent at least. So I more think the maximum is 12 out of 12, but what's the lowest possible number? Now, to get the lowest possible number, really, I care about how much of these fragments I could be getting to overlap. Because if I had the identical 6 letters, then I would say that they could only represent at least half, because there's a possibility that they're actually just the same fragment. So I'm caring about how much overlap there is. So we've got ATT, GAT, and then ATATTG. So there's a possibility, what I'm looking at is like if I lined this up here, that could work. It could also go ATTG, but the one in blue is more overlap. So if that was the case, that means the 2 sequences would represent, how much is that? That's only 8. That's only 8 base pairs. We got 1, 2, 3, 4, 5, 6, 7, 8. So once we've accounted for the overlap, that's 8/12 of the sequence, which is answer A. Okay, 74. Radioactive materials, blah, blah, blah. So this is quite similar to the one we just did with half-lives, actually. So a radioactive material, so it has, I think this will be going in the opposite direction though. So half-life of 10 minutes. So how long will it take for 90% to be transmuted? Now I'm just going to assume transmuted means broken down. That's the only thing that would make any sense here. So for 90%, so again, we go 100 to 50 to 25 to 12.5 to 6 point something. So it's between 1, 2, 3. It's greater than 3. So it's between 3 to 4 half-lives, which is between 30 to 40 minutes, which is answer option B. And last question. In order to undergo a scan, a patient is injected with a radioactive isotope that has a half-life of several days. Doesn't seem to make sense. If 1%, it says it has a half-life of several days, but after 13 or 14 hours, 1%'s left, but whatever, we'll go with that. So we'll just continue on. I won't do a new one. So it said that there's 1% left. So it's like 6.75 or something. So it's like 3.2 to 1.6 to like 0.8, something like that. So that's 5, 6, 7 half-lives, I believe. So we need 7 half-lives, and the total time is 13 to 14 hours. So I think the best estimate would just be 2 hours. So 2 hours, be like 2 hours here, 50, 20, after 4 hours you'd have 25, after 6 hours you'd have 12.5, 8 hours you'd have 6.75, 10 hours you'd have 3.2 or whatever, 12 hours you'd have that, 14 hours you'd have under 1. Perfect. So that's answer option B. Whew. So, bit of a marathon there. I don't know how long this video's ended up, but it's certainly a lot longer than I thought it would be. Some tricky questions in there, but I think ultimately, I think it's exactly the kind of stuff that I think you need to be practicing. So I'll make another video reviewing all my answers, seeing how many I got right, and probably reviewing the ones I got wrong and seeing where I went wrong in that process. But I need to have a little GAMSAT break, I think, after this marathon. So I hope you enjoyed seeing me go through all those questions, and yeah, I hope it helps you with your study.